So today I'm gonna talk about directional maximal operators in Kakeya-type sets, which is a work together with my PhD advisor Paul Hagenstein and Alex Stokolos, who was here in the conference in the previous days. If you never hear about directional maximal operators like Kakeya-type sets, let me just start with a theorem that I'm pretty sure that everyone already knows, which is the Lebesgue differentiation theorem. And just a recall is, well, we are gonna set an little n, a natural number, which in this talk will represent the dimension of the space. And if we consider a function f in L1, for almost every single point in the space, if we consider the average of the function over ball centered at the point x and radius r, and we are shrinking those average or those balls, basically considering the radius goes to 0, it converges to the value of the function at the point x. Okay? So this is a theorem that everyone see in our real analysis class, right, when we are students. And if you recall, what is the proof or how we prove this theorem is thanks to the Radillo-Maximal operator, which is defined almost in exactly the same way. Is also considered an average now of the absolute value of the function f over those balls, but now instead of taking the limit when the radius goes to 0, it's considering the supremum over all the possible radius. So it's considered the supremum of the average of the function. Okay? And we have the Lebesgue differentiation theorem for functions in L1 because the Radillo-Maximal operator, it is something that we call weak type 1-1, or basically is that we have an estimate on the set of the points where the maximal operator is greater than a constant. So it's more or less like a Chebyshev inequality. So the measure of the points where the maximal operator is greater than some alpha, some constant alpha, is less than or equal to some constant that will only depend on the dimension n times the L1 norm of the function over alpha. And this needs to be happen for all positive alpha. So this is the weak type 1-1 estimate. So basically we have the Lebesgue differentiation theorem takes to the boundedness of this Radillo-Maximal operator, but because the Radillo-Maximal operator is a sublinear operator, basically we can, from the definition, we can see that it's also bounded in L infinity, something that we call a strong bounded or just bounded from L infinity to L infinity. And thanks to interpolation theorems, we can recover all the LP spaces between, well, P between 1 and infinity. So at the end of the day, the Lebesgue differentiation theorem is still true for functions in LP, for P greater than or strictly equal than 1. Okay? So this gives us an inspiration of studying maximal operators defining as an average, but maybe do not consider balls. What happens if we consider average over other type of sets? Right? So this gives me the question or the problem that if we consider R to be a collection of open subsets, and let's just avoid more problems or more issues, and let's put the condition that these subsets needs to be positive finite measure. And so the question is if there exists a P such that the associated geometric maximal operator in defining in the same way of taking the average of the function f over those open subsets, it will be bounded from LP to LP. Right? So at the end, this question, it will be, all the philosophy of this problem will be actually behind on or lying on the geometry of the collections that I'm taking the average over. Okay? So let's look at some examples. And well, of course, the highly maximal operators, it will be considered balls And we have the boundedness. We have with type 1 bounded, but at least the struct boundedness from LP to LP for p greater than 1. When you harmonic analysis, we learn also the definition of the Radillo-Maximal operator and center one, which is now considered balls with not necessarily the center to be the point X, and is still true. And also, if we consider cubes in Rn, and well, at least consider cubes is exactly the same result thanks to the relation between balls and cubes, right? Like we can put a ball inside a cube and a cube inside a ball. And so basically we have exactly the same thing. So what happened if we consider, for instance, boxes, right? So boxes in Rn, and now I don't have restrictions on the sides, but I'm so far I will put restrictions on the direction of those boxes. And if we consider the maximal operator associated to the collection of boxes, but whose sides are parallel to the axis, so now the directions are, well, if it is in Rn, we have only n directions, one for each coordinate axis. So it has a special name, which is a strong maximal operator. And this operator is not weak 1 bounded. So if we consider the Lebesgue differentiation theorem thinking as average over boxes, it won't be true if we consider a function in L1. But good news is that this strong maximal operator it's bounded from LP to LP for P strictly greater than 1. So again, we are recovering Lebesgue differentiation theorem, but now for P strictly greater than 1. Right? And it's been proven by Jensen, Martin, Kevins, and Sigman in 1935. And with a different proof, Antonio Cordova and Robert Pfefferman in 1975. Right? So if we input in more or different kind of directions, we might have, or this problem has more difficulty. The good thing of talking about boxes with sides parallel to the axis is because basically we can use Radillo-Maximal operator boundedness for each direction and just iterate it. So, so basically we have for granted the size parallel to the axis tends to the Radillo-Maximal operator, but if we have different directions, we might not be able to do this interaction per direction or per axis. So one of the easy or one of the following natural example for thinking about maximal operators, it will be considering directions in a lacunary way. And so just a definition, the lacunary, we say that we have a lacunary sequence, and this sequence, let me call it capital omega, and it's going to be numbers theta j, numbers between 0 and 1, so that will represent my directions. Now I'm thinking directions as the slope, right? So it's in centroid way, we have a axis for those boxes or those rectangles, and that will be the slope. And I said that this sequence is lacunary if, well, of course, just put in an order. I'm gonna say that is descendant sequence, and if there exists a constant between 0 and 1 such that the difference between two consecutive numbers, it's more or less, or is equivalent to that constant times theta j times one of them. One classical example of a lacunary sequence is the powers of 1/2, right? 1/2 to the minus j. So what if I'm talking about the maximal operator associated to these directions? Well, if we are consider boxes in Rn, well, we have different angles, right? So it depends on where, from which plane I'm talking about, having the angle. So far for this talk, I'm gonna just make it my life more simple, and I'm gonna talk about R2. So now my boxes are going to be rectangles, right? And the directions, it will be in the natural way, the slope of those rectangles, right? The slope of the longest side of each rectangle. And so if we consider a lacunary set omega, and we consider all what are like, or are lacunary, the family of rectangles in the plane, whose slope is in omega, and if we consider the maximal operator associated to this collection of rectangles, and we call it the lacunary maximal operator, good news is we have exactly the same properties as the strong maximal operator, the one that has sides parallel to the axis, which is it will be bounded from LP to LP for P greater than 1, and is being proven by, again, Antonio Cordova Robert Pfefferman in 1977, Stroman in 1977, and funny thing is, these two results are thanks to covering lemma, so it more or less bringing back to the philosophy the Radillo maximal operator, who was proved using Vitalik covering lemmas. We can have some certain covering lemmas for rectangles, but the only complicated part is that these only prove the range of P is strictly greater than 2. But Nagel, Stein, and Weiner 1 year after recover the whole range for P greater than 1, thanks to Fourier analytic techniques, right? Talking about multipliers and so on. So, but Jolene and Jagrin, two good students, mathematicians, extended D out to be a lacunary set with higher order. So basically what it means is, we need an extra definition before to explaining that, but basically is we will call two sets, E and E prime. It needs to be null set. So it's in some way thinking that it's going to be countable. We say that E prime is a successor of E if there is a constant such that for any 2 points in E prime, so in my brain thinking E prime, it will be like a higher subset or a higher set, and I'm taking 2 points X and Y. So the distance between these two new points is going to be greater than a constant that is going to be fixed times the distance from one of the points X to the set E. So that's what it means, the E of X, the distance of the point X to the set E. Right? So it's basically adding and adding more points. And so this helps us to define what is a lacunary set of higher order, which basically is, well, we are going to say that is a lacunary order 0 if the set it contains only one single point. And if we said that is a lacunary sequence of order n if it is a successor of lacunary set of n minus 1. So basically an example, a natural example, it will be, well, we consider previous definition, the set of 1 power of 1/2 or a powers of 1/2 will be lacunary set of order 1. And if we consider the type of numbers that are the sum of two different powers of 1/2, it will be a lacunary set of order 2. So basically it's more or less like how many powers of 1/2 do I need to describe the full set of numbers. So that will be the order of lacunaricity of this set. Right? And this gives us a good extension because if we consider again the associated directional maximal operator to a lacunary set of finite order n, and again I'm talking about the plane rectangles in the plane orientated to those directions. Luckily, it's exactly the same result. Maximal operator will be bounded from any LP for LP to LP for P greater than 1. And years after, in 2015, 10 years ago, two good mathematicians, Javier Parcel and Key Rogers, introduced a way of thinking lacunaricity in higher dimensions. So now we can be back on the question of boxes, and they had exactly the same result, that they bound the maximal operator will be bounded from from LP to LP to P greater than 1. We are losing already thinking about weak type 1, but now the remaining question is, what can we say about the non-lacunary case, right? And for starting in a good way of thinking, or analyzing this case would be, well, let's start with a simple example of a non-lacunary case. Well, non-lacunary, what I mean is not like it's not lacunary of finite order. So I need infinity many powers, or 1/2, or whatever rational number that I'm taking, or actually whatever number I'm taking to describe the numbers of the set. So one classical example to be non-lacunary or non-lacunary of finite order is the Cantor set, because I need, well, infinity many powers of 1/3 for describing all the numbers of the Cantor set, right? For some of them, I just need a finite number of powers of 1/3, but I mean, for any random point in the Cantor set, I will need the infinite expansion, right? And what is going on with this maximal operator associated to the directions of the Cantor set? Well, in a big contrast with the lacunary case, Michael Baymans and Ned Scott in 2008 proved that the maximal operator associated to those rectangles whose directions are in the Cantor set will be unbounded for every single finite p. Right? So, so basically, at least in the plane, we have, looks like the problem is, if it is finite lacunary, I will have boundedness, but if I'm losing lacunaricity, I might have, or also lose the boundedness of the maximal operator. Edward Krog and Malavika Pramanik in 2016, for Edward Krog PhD dissertation, they extend the idea of the result of Michael Bayman and Ned Scott in higher dimensions. So they define also a type of directions of those boxes in a Cantor type way. Okay? So basically, this is directional maximal operators, but you were wondering, like, well, what is going on with the Kakeya-type sets on my title, right? So basically, they prove that those maximal operators are unbounded thanks to that the Cantor set admits Kakeya-type sets. And if you never hear about Kakeya-type sets or Kakeya sets in general, let me just describe what they are. So we will say that a set of directions admits like a Kakeya-type. Oh, I only have 2 minutes, right? So a Kakeya-type set, if I consider the area of the union of the rectangles, and I compare that area with some dilation of those rectangles, so I'm making them bigger, and the area of the union of the dilation, it will be bigger than every single n. I mean, every single n multiplied by the area of the rectangle. So basically, they are growing huge and huge and huge, right? So why this affects that the maximal operator will be unbounded? Because now if I consider the characteristic function over the original union of rectangles, well, it will be greater than a constant that only depends on the dilation. Actually, it's like a 1/c when c is the dilation. And if I consider the maximal operator acting on that characteristic function, and of course for making computing the bounding of the operator, do the quotient, n will be bigger than any single n in natural number. So basically that gave me, and I don't have time, I was talking too slow, but at the end of the day, what we can prove is, there you go. So basically we can extend, that's the work that I was doing with Paul Higgins and Analysis Stokolos, is we can generalize our set of directions, and it's something that I call, I don't have time for explaining what is a eta separation tree, but at the end of the day it's more or less the same as the Estes Cantor set. The only difference is when I'm doing the interaction of the Cantor set, I don't care if it is the same size when I'm choosing the intervals. It can be one extremely small comparing to the other huge one. The only important part is that the distance, the Euclidean distance between the two ones that I'm choosing is eta separated, or is a eta constant. And I will have exactly the same result. The maximal operator will be unbounded from LP to LP. The remaining question is, if the set direction doesn't have separation, is still an open question. So everyone is welcome to working in this area, and thank you for your attention.
Thank you, Blanca, for nice talk.